Okay, so welcome back, and now we're going to do another example, but this time we're going to deal with satellite. So let's say we have a satellite that's orbiting, so here's my little satellite, and it's orbiting the Earth, and the satellite is 22,320 miles above the Earth, and the radius of the Earth is 3,960 miles. And we want to find out how fast is this satellite moving. And so this is going to be angular velocity. Now, the thing is we don't have any other information, but let's think about this. We know, first of all, we're told that it's moving along the equator of the Earth. And so we know that, and that's important to know because if it's at the equator, then as it travels around for one day, it has to travel. It's going to have to take the same amount of time, right? If it's traveling around the equator of the Earth, right? And it must remain at the altitude given. Right? So in order for the satellite to remain over a point on the equator, right? So again, we're assuming that it's staying at that point. It's got to rotate. It's got to rotate around exactly in one day, right? So again, the Earth rotates one full time in a 24-hour period. So the satellite, in order to stay right above the same point, it has to rotate around the same distance, right? Assuming it's at the same distance all the way around, it's got to rotate and come all the way around in the same 24-hour period. Okay, well that gives us something to work with. Because we then know that one full revolution around is going to be 2 pi radians, right? Okay, and let's see. So one revolution would be 2 pi radians. We got that. And one revolution is equal to a day, right? So let's write this down. So one revolution for each day. We also know that there are 2 pi radians for each revolution, right? And we also know that the angular velocity is equal to what? Theta over t, right? Okay, well, let's put this together. So, the angular momentum is going to be the theta over time. Well, what's time? Well, we know we go 1 revolution for each day. And 1 revolution is the same as 2 pi radians. So what does that mean? It means that I can say, if I want radians per day, right? I can say, well, multiply these together. And so that gives me what? That I get there are 2 pi radians for each day. But a day is 24 hours, right? So this is going to be 2 pi radians per 24 hours. So this is the angular momentum. 2 pi radians every 24 hours. And so if we stick that in our calculator now, because again, we want radians per hour, right? Or well, do we want revolutions? Let's just radians per hour. Okay, so we get 0.2618. 0.2618 radians per hour. That's the angular velocity. Okay, now that we got the angular momentum, let's find what the speed of this thing, the linear velocity is. So now we know how fast it's moving, the angular momentum. Let's find out how fast this thing is moving at that altitude as far as linear velocity. So now we're going to use the radius. Now, what is the radius of the circle? Well, it's going to be the path of the orbit of the satellite. So that's going to be this plus this. So the velocity of the satellite is going to be equal to omega times r yeah, that's right. So omega times r, and of course omega is equal to 0.2618, and the radius is given to us as this plus this, which is going to be 26,280 miles. And so this is radians per hour. This is miles, so we're going to get miles per hour. Let's see how fast this satellite is moving. So if we calculate this in our calculator, it is approximately 6,880 miles per hour. So approximately 6,880 miles per hour. And that's what you have. Have a great day.